Okay. For those of you that joined me yesterday, it was very fast and precise. This is question number 1 for those in Hall 1. And it states that what is the secondary impedance of transformer whose transformer ratio is 0.2? The primary current and voltage are 5 amps and 24 volts respectively. So you can see very well that from what we have, the solutions are very simple. First of all, you put up the known variables, which is the transformer ratio 0.2, the primary current, which is 5 amps, the primary voltage, which is 24 volts. Then your unknown variables are the primary impedance and the secondary impedance. But what we are told to check is the secondary impedance. But you can't check secondary impedance without getting your primary impedance. So having done that, we use Ohm's law here in order to get our primary impedance, because we have the variables that we use to get the primary impedance while using the Ohm's law. But in this Ohm's law, you notice that R changed to Z, which is impedance. R changed to Z, which is impedance. So with that in mind, we will now say that primary current is equals to primary voltage all over primary impedance. And when you make the primary impedance subject of the equation and you calculate through, what we will have is 4.8 ohms. Then 4.8 ohms becomes our primary impedance. Then getting the secondary impedance, we use the transformer ratio, the impedance ratio of a transformer, which states that the square of the transformer ratio is equals to the primary impedance divided by the secondary impedance. And with that, if we make the secondary impedance, I hope you are seeing my mouse. I hope you are seeing my mouse.
Yes, sir.
Okay.
Yes, sir, we can see it.
Okay. If you make the secondary impedance subject of the equation, it will now be primary impedance divided by square of the transformer ratio. And when you do that, you have 120 ohms as the secondary impedance. So for question number I1, number 1I, which this thing should go now. Hold on. Okay. And this one is what type of transformer is the transformer in question 1? We know very well that the type of transformer is what? Who can answer it? Who can answer it?
Step-down transformer.
Is what?
Step-down transformer.
Amugamba is not step down. In the
It's step
class,
up, step up transformer, because the secondary is lower than is bigger than the lower system. It's bigger than the primary.
okay, one of the reasons you should know, even by mere looking at the transformer ratio, is that for transformer ratio less than 1, they are always step-up transformer. For transformer ratio greater than 1, they are always called step-down transformer. Are you getting me? That's the mathematical interpretation of what we are doing. Then for question number 2, what type of magnetic material has its relative permeability to be 10? You know that the relative permeability that are greater than 1 are for ferromagnetic material. The ones that are greater, like slightly greater or equal to 1, they are paramagnetic material. Then those that are slightly less or equals to 1, they are called diamagnetic material. Therefore, this magnetic material is a ferromagnetic material. You see, the questions and the answers are very simple. Some of you did not even write anything. Are you getting me? Some of you did not write anything. And the implication why I have to put up that quiz is to match up your attendance, to use it as an attendance. You see that the questions are 3. If you get 3, means that you've gotten 3 attendance. So for question number 1, say define magnet and differentiate between magnetic materials. And we know very well that magnets are those materials that has the ability to attract or repel other materials within its line of force. It has a north and south pole, where magnetic line of force originates from the north pole and enter back through the south pole. So that's just the brief of definition of magnets. Then magnetic materials, we have the ferromagnetic material, we have the paramagnetic materials, and we have the diamagnetic materials. Then for ferromagnetic materials, we have that their permeability, their relative permeability are far more beyond 1. They are in thousands. That is, their permeability are in thousands, while that of the para, they are slightly above 1 or equals to 1. Same goes to the ones with diamagnetic material, which is less than 1, or equals to 1. Then for ferromagnetic materials, they are very strong and does not lose its magnetism. They magnet without external forces. But for paramagnetic material, they are slightly strong and cannot easily lose their magnetism. This one cannot easily lose. But in dia, they can easily lose their magnetism and they are very weak. So the materials for ferromagnetic material are iron, cobalt, steel, nickel. Then for paramagnetic material, we have aluminum, calcium, titanium, and copper alloys. And we have copper, silver, alumina, and silicon for diamagnetic materials. So that's that for question number 1 for those in Hall 2. So for question number 2, for those in Hall 2, you people should better mute your mic. Hold on. So the question says that, what is the ratio of transformer whose primary turn is 50 turns and secondary turn? Who is this person? Abonyolu Ebube. I'm removing some of you people. So in this case, you use your transformer ratio equation, which states that I don't know who is this person joining from YouTube or whatever. I can't tell. So we use this equation, V of P over V of X is equals to number of turns at the primary over number of turns at the secondary. Then what we are given, the variables we are given are the number of turns. So in that case, we can use the number of turns to calculate our transformer ratio. And that gives us 0.4167. Or you can abbreviate further to get 0.412. That becomes your transformer ratio. For question number 3, using the transformer ratio of question 2, determine the primary impedance when the secondary impedance is 100. Very simple. You state this equation, the impedance, transformer impedance ratio, which states that the square of transformer ratio is equals to the primary impedance divided by secondary impedance. You are going to pay for this data together with those of them yesterday. So having this, we will now have that the primary impedance is equal to the square of the transformer ratio times by the secondary impedance. And that gives us 17.36 ohms. A lot of you got this question, but some of you are trying to copy and copying rubbish. So this one is for question number 1 for those in Hall 3. I say using a simple diagram, explain magnetic flux line and neutral points. So this is a simple diagram of two like poles of magnets. Neutral point of a magnet can be created when the two like poles comes together. This is magnet A and this is magnet B. And we're going to remove that in your sharing screen, or I will delete you from this platform. So magnetic flux line are the line of force of a magnet. It surrounds the magnet and determines the strength of attraction or repulsion of a magnet. The line is concentric, meaning that it's circular. Each of the lines are circular, originates from the North Pole and enters through the South Pole and is continuous in nature. So each of the lines are equidistant and they are perpendicular to each other. Each of the lines are equidistant and perpendicular to each other. Then I've explained most of these things. You can just look at it and read it. Then when two like poles are brought together, they intend to deviate from each other, like repulsing each other, thereby creating a point where the effect of a magnet cannot be felt or where you cannot experience the magnetic attraction. And that point is called the neutral point. So this one is question number 2. Explain why power can never be transformed by a transformer.
You're not seeing the edge.
The edge of what?
That thing is not showing well.
What thing is not showing well? The question.
Everything, even the answers. Did he use to cut?
Use 2 fingers and minimize it now. Like zoom it in and zoom it out.
Thank you, sir.
You're welcome. Please mute your mic. So explain why power can never be transformed by a transformer. So recall from the transformer equation, these are the transformer equations that we've been dealing with. Yeah? Where VP is the primary voltage, VS the secondary voltage, IX secondary current, IP primary current, the alpha transformer ratio, NP primary turns, and NS secondary turns. So using this equation, we have that VP is equals to VP over VS is equals to IS over IP. And when you cross multiply, you will see an equation where the primary power, this is the formula for power, we all know that. Power is current times voltage. is equals to the secondary power. And I equally further explain that from the above equation, when transformer voltage is increasing at the secondary side, its current is decreasing at the secondary side. And vis-a-vis, I mean that when the transformer current is increasing at the primary side, its voltage at the primary side is equally decreasing. Then question number 3. What is the magnetic intensity of a magnet with flux of 5 Weber, 50 Weber, and cross-sectional area of 12 meter square? So, from the magnetic intensity equation, which is B equals to phi over A. B is the magnetic intensity, phi is the flux, and A is the cross-sectional area. B is what we are looking for. We have the phi, which is 50 Weber, and we have A, which is 12 meters square. And when you put them together and divide them, based on this equation, we have 4.1667 Weber per meter square. So if you have any question, you can ask so that we deal with it now. You can unmute your mic one at a time, or you raise your hand, I will tell you to unmute your mic.
So please, can you explain why this power can never be transformed by a transformer again?
What's your name, please?
Ajewale Steven, sir.
Adewale Steven. Okay, Adewale Steven. If you look at this equation very well, these are the equations all of us are familiar with. That the voltage at the primary over voltage at the secondary, we can use it to get our transformer ratio. So what this means is that when we put these two things together, they say they are equal because they are equating to transformer ratio. Are you getting me?
Yes, sir.
Okay. So when you bring them together, like when you make VP over VS equals to IS over IP. From here, hope you are seeing my mouse.
Yes, sir.
Okay, I'm using this mathematical equation to explain this to you. So what it implies that VP over VS is equals to IS over IP. When you cross multiply them, what you will have is VP times IP is equals to VS times IS. And I said that power from what you did, which department are you?
Dental Tech.
Okay. You've done power in your first semester, which we define is that power is current times voltage. I gave you so many formulas for power, but this voltage times current is the one that we say is sacrosanct. Others are derived from it. Are you following me? So you can see that the power at the primary is equal to the power at the secondary. And I now further explain that from the equations you are seeing, it's telling you that when the current at the secondary is high, the voltage at that secondary is reducing in order to balance up, to make up the power to be equal to each other.
Yes, sir.
Okay. Any other question? Any other question? Any other question? If you have question, you unmute your mic and ask the question.